As Natalie said, I'm going to talk on the topic whether genetic testing for sporting injuries are premature. And I have spoken before on this topic, and there's a fair amount in the literature of opinion pieces of trying to address this issue in response to commercial companies that are trying to market these tests. But nobody has actually ever, to my knowledge, ever done an analysis of the tests that are done and what is the evidence for the various genes or genetic markers that have been included in this test. So that is what is going to be new about the presentation that I'm giving today, and it's a summary of the analysis that Alison and I did last year. So why is this topic relevant, and why have several companies around the world commercialized tests? And the reason for that is that susceptibility to various musculoskeletal injuries are what we call multifactorial. They are determined by a complex interaction of genes and the environment. So both nurture and nature will predispose individuals to these injuries. It's not nurture or nature, it's both. And because there is a nurture component, a genetic component, and in some cases it's been estimated to be quite large, there is an interest then to determine or to market tests to just use the nurture aspect to determine whether you're predisposed. Just to remind you all that our human DNA is 99.9% identical. Alison and I and others were at the International Conference of Human Genetics last week, and this issue was brought up many, many times, that we as human beings are identical for all practical purposes. What? Boringly. We are boringly, and if some Martian came from outer space, they would think that we are very boring. I think somebody used that analogy. However, although our DNA is 99.9% identical, there is a 0.1% difference. And this 0.1% difference plays a very important role in determining the inter-individual variation that you see amongst us or can measure amongst us. So we look at this room of people sitting in this room. We are boring, as the geneticists say, but we all look different. So we are uniquely boring. And that uniqueness is partly determined by this difference that we see amongst us. And we call these differences mutations or polymorphisms. And I'm just going to use the word variance for the rest of this talk. So as I've said, musculoskeletal soft tissue injuries are multifactorial. Here's an example of tendon injuries. So the classical model will divide the various risk factors into what are called your intrinsic risk factors. Those are the factors that are part of us, that we are born with. There's very little that we can actually do to change them. And then there are the extrinsic risk factors. Those are the things that are outside of our body, which can determine our susceptibility to injury. And it's a combination of these intrinsic and extrinsic risk factors which determine susceptibility to whether or not we ultimately become injured. I'm just checking for the sports edition that I am being accurate here. He gave me the thumbs up. And so this is a classical model. If you take ligament or ACL injuries, it'll be similar. If we take muscle injuries, it'll be similar. It's just there could be subtle differences between the extrinsic and intrinsic risk factors, which are often injury specific, but there often is an overlap in the types of risk factors that are listed for the specific injuries. What this graph shows, or this diagram shows, is that if you look at the intrinsic risk factors on the left, that virtually all of them are to a less or greater extent also what we call multifactorial phenotypes. So we look at height. Height is determined, over 80% of our height is determined by our genetic makeup, 20% by our non-genetic makeup, mainly, and the dietitian sitting here, the food that we eat. So that determines height. We take many biomechanical properties, anthropometric properties. There's both a genetic and a non-genetic component, which determines ultimately what it looks like or its outcome is going to be. And so there is a genetic component. And so this is the classical way in which the intrinsic and extrinsic risk factors are drawn. But now people are starting to realize that it's not as linear as people thought. And so people are starting to use, and I need my glasses on because I can never remember, using complex systems approach to develop, and this is a hypothetical diagram for injuries, to understand that there's this web of interaction. And it's very complex, and we don't fully understand it, which will determine susceptibility. Again, our intrinsic, extrinsic factors, and then many of the intrinsic factors I showed at the top there are determined or partly determined by our genetic makeup. And therefore, there's inter-individual variation in our susceptibility to injury. So here is a hypothetical diagram. At the bottom is the uninjured state below the bar, and above the bar is the injured state. And it's often the load or the force and the frequency which determines together whether you become injured or not. And the red line, unfortunately, are the people that it takes a lower load and frequency to become injured. And the green line are people that can sustain a higher load or frequency before they become injured. And so that, in many of the textbooks, they just have a single line between the injured and uninjured state, but it should actually be a band, because that band is determined by acknowledges the inter-individual variation between individuals. So we're not identical. Our tissues are not identical. Our tendons, our ligaments, there is biological variation in structure, in its biomechanical properties, and therefore how it responds to load, its susceptibility to injury, and another thing which is related, healing and repair. And so we and others have proposed, and when we started this work, that there are these variants within our DNA, these so-called polymorphisms, which will predispose certain individuals to specific injuries. And the theory was that if we understood this and really got to know what are the variants, the genetic variants, which predispose individuals to a particular injury, you could take a population of athletes. You could then use genetic testing together with other risk factor identification, and then stratify them into high, medium, and low, or whatever form of stratification method that you want to use. And then what you could do is take the high-risk individuals and then personalize their training, and I'll talk about this practically how we could do this today right at the end, to minimize risk. You can never totally get rid of risk, but you can minimize risk to injury. So that's my introduction. So as a result of this, there are many companies around the world who are called direct-to-consumer genetic test companies, or DTC companies. And these companies usually market their tests via the internet, television, the print media. 23andMe, I think, is one that you've all heard about. People today want to know about how much DNA they have from Europe, from Africa, from Asia. It's now become cool to know what the percentage of Neanderthal or whatever we are. I'm boring. My sister did her, and we just very boring. the problem with these tests is they are not marketed the traditional way that a genetic test is marketed. A genetic test is usually marketed traditionally through a healthcare professional. So you'll go to a doctor. That doctor will do a proper examination, take your history, do special investigations, and might say, actually, we need to do a genetic test. That test is done, the result goes to the doctor, and the doctor, together with other appropriate health care professionals, will interpret those results for you in the context of the larger clinical picture that is presented. That step, that important step, is often omitted, or for all practical purposes omitted in these DTC tests. The type of claims, and here's one, a South African company, DNA Lysis, and they will claim as a result of their test, we can determine a susceptibility to injury risk, power endurance potential, your athletic ability or potential, peak training time in response to training, and our recovery time. So the number of claims that are made by these companies ranging from our ability to susceptibility to injury, and I'm going to concentrate on this talk to susceptibility to injury. So when we look at the list of companies, and I'll show some more detail later, the typical marketing claims for injury range from non-specific statements like, as a result of this test, we can determine soft tissue injury risk, risk for inflammation and injury predisposition. Up front, I want to, and Darun, I think, can correct me here, whenever you make a non-specific claim, run a mile away. Because a non-specific claim suggests or implies that the etiology is similar and that there's homogeneity with all injuries. I am not a clinician, but I know enough to know that all pathologies are not the same. Even if you speak to cancer biologists, it's becoming far more heterogeneous than we probably thought it was years ago. When it comes to injury, there's huge amount of heterogeneity. Am I correct, Jareen? And so any general statement upfront is misunderstanding mechanism and the clinical picture. So other companies have very specific statements: Achilles injury risk, ACL injury risk of stress fractures, risk of muscle cramping, as a few examples. So here, at least that is going correct and understanding the heterogeneity of the injury and specific, but I hopefully will be able to prove you that it's still premature to do the genetic test to here. I've highlighted two broader statements from two of the companies, which says the athletic report analyzes over 75 genes and provides insight into 40 traits related to physical fitness. These traits include connective tissue injury risk, back injury risk, bone and joint injury risks. Okay, but nowhere on their site do they say what those 75 genes are. So you are unable to make an informed decision of the accuracy or validity of those tests. This to me is one of the best ones. This company's genetic tests are based on peer-reviewed studies published in the top scientific and medical journals, giving our products an indisputable seal of credibility. So I went to look at their reference list to see which were these top journals, which Vicky explained so eloquently as are, and not one of them was listed. In fact, I think there were pictures of them, but I know that not one of those journals has published an article on any of the genes. They didn't mention the genes, but they're not the standard journals that publish on sports injury genetics. So that's a little bit misleading. In fact, it's very misleading. So here's a typical result of a direct to consumer company. So here they have done a test, and this is one of the genes I'm going to be talking about. In fact, all three of those, three genes that they include. I'll explain in more detail what they are later. And based on their genotype, they were able to say your genetic results indicate that you likely have a moderate risk of developing soft tissue injury. And then they go on explaining what that means. So the first half of that talk, I'm going to focus on these three genes and to say what is the evidence for including them in a genetic test. And another reason why this is an important topic is because over the years there's been hype in the media over it, where top BBC, the Sunday Times, that's the London Sunday Times, apparently a top publication, talk about international teams in the UK using these tests to determine susceptibility. So what did Alison and I do? So we went to the literature and we went to the web, and we identified all the companies around the world that market genetic tests for injury. And we were able to identify 10. So around the world, there are 10. What is interesting from the analysis is that in the original lists that were drawn up, there were over 20 or 30 companies. Over half of those companies no longer exist. And out of the remaining, most of them, not all of them do genetic tests for injury, only a subset do. They focus on performance. But these companies are the ones that do injury. A lot of the companies, as you can see there, we could find no evidence of what the genes were that they are testing. So they make these claims, but we have no idea what they're actually measuring or genotyping the people there. So it's non-specified. In fact, two of them, which I've got the markings, had those statements in that previous slide. Those that do specify, most of them use three genes: COL1A1, COL5A1, and GDF5. And I've highlighted those there. In fact, all the original work done on those three genes was actually done in this building. So my claim to fame, one of my claims to fame, is I'm the source of bad commercial products. What? And you go to these, and when you reference, it's not nice. At any rate, so those are the three main genes which are used by several of the companies. There's one company which I'm going to talk at the end about and just highlight. It's called Axgene, and they're the only company that uses injury-specific polymorphisms that have been identified by genome-wide association studies on very large population groups. So they are the only one that is using that approach, but even that I will show there are certain issues related to that. So as I mentioned, there are three genes which have been used by most companies, and here's an example of which I showed earlier of the result given from those three genes. So I'm going to very briefly just go through the evidence for those three genes before I talk about the GWAS studies. So the first is COL1A1, a COL1A1 variant with that number. So for those who are not geneticists, all the variants within our DNA has a tag or a number to identify. Like you've got a name. There's Alison. So RS180012 is just the name of that variant, and I can go into Google or to databases and it'll give me all the information for that. So that's just its name, okay? And as scientists, we are boring, so it's the reference number. At this variant, there's a G or a T. Now, remember, we inherit two copies of most of our genes from our parents, one from mom and one from dad. So each of us at this variant there are three possible combinations. We can all have a GG, a G from mom and G from dad. That's homozygous, GG genotype. Or we are TT, T from mom, T from dad. That's TT homozygous genotype. Or we have a G from dad or mom, but a T from the other parent. And that is heterozygous GT. So just to remind you that. Now, the COL1A1 gene encodes for a structural component of type 1 collagen, one of the alpha chains, and type 1 collagen is the major building block of tendons, ligaments, and other connective tissues. This variant is also functional. It is found within a regulatory region of the gene and plays a very important role in controlling transcription. Transcription is the amount of RNA that's produced from the gene, and then the amount of protein that is produced. And by altering the amount of protein, you can change the composition of type 1 collagen, and by implication, the biomechanical properties of the tissue. So this is a functional polymorphism, and it's in a regulatory region. So it's a good candidate. So if we have a look at the literature, several articles have looked at this variant and its association with various musculoskeletal soft tissue injuries, in particular ACL injuries. And what we generally are finding is that the TT genotype is associated with reduced risk of acute injuries in European populations. Okay, so now I need to just backtrack when it comes to the variation of variants in different populations. They're not the same. Okay, they're not the same. And so most of the studies which have looked at this variant, and we've done combined analysis of looking at all the studies that have done, that this variant, in particular the TT genotype, is associated with reduced risk of ACL, but it looks like more broadly to all acute injuries and I specifically going to say in European populations. And the reason I'm using European populations, because the T allele, and therefore the TT genotype, is more common. It's rare, but it's more common in European populations than in other population groups. In fact, in African populations, it's only 0.5%. American, that's Latin American, 2.3%. East Asian, it's absent, and 1.2% in Southern African populations. So in other population groups, this variant is not associated. And the reason for that, it's just not informative, it's too low. And so it appears also not to be associated with chronic injuries. The sensitivity is also very low in the European populations, less than 1% if you do the calculation. And so it is premature, therefore, to include this variant as a marker for injury risk, because it's just not good enough. Okay. The second one is COL5A1. Again, that's the marker, the name of the marker, and there it's a C or a T, so you can be CC, CT, or TT. COL5A1 encodes for a structural component of type 5 collagen, and type 5 collagen is functionally an essential component of the collagen fibril, the collagen fibril being the basic building block of ligaments, tendons. So in brown, there's type 1. In blue, there is type 5 collagen. This polymorphism is located in a functional region of the COL5A1 gene. And we believe that it plays a role from the work that Nancy did. I forgot your name there, Nancy. Mary Jessica, in altering mRNA stability of the COL5A1 gene, and then by implication, the structure of this fibril and the biomechanical properties of the tissue. So what's the evidence? So here is a very busy slide, a slide which I'm not going to try and dissect you, but that busyness and complexity should answer the question. So these are the main points that come out from that slide. The variant has been associated with the modulating risk of Achilles tendinopathy, tennis elbow, and carpal tunnel syndrome, but not, so those are more chronic injuries, but not your acute injuries. Generally, the CC genotype is protective and the TT genotype increases injury risk. However, and this is important, there is no consistent pattern. And because there is no consistent pattern, it is premature to include it in any injury test. Okay. There are many genetic markers which have been identified. And this slide just shows the complexity. I've focused on 2 structural proteins, but there are regulatory proteins. And GDF5 is one of the regulatory proteins which regulates connective tissue and regulates tendons and ligaments. And so this is where GD5 comes in. It's a growth of differential factor 5. It is also a functional variant which regulates transcriptional activity, so the amount of RNA that is produced in the cell and by implication the protein. There are only 3 studies that have actually looked at this polymorphism and musculoskeletal soft tissue injuries. Most of the results show that the TT genotype is associated with increased risk of injury. However, only 3 studies, small sample size, and this genotype, which is associated in some of those 3 studies, is absent in African populations. So a whole percentage of the world's population, it would be meaningless to include in this test. So again, premature to include this variant as an injury marker. So those are the 3 markers that a lot of the companies use, and probably the 3 most commonly used markers. From a scientific point of view and investigation of understanding mechanism, they are important to investigate. But there's a big difference between doing scientific research and including something as a marker for a condition commercially. Because there you are making more absolute statements. You are at risk or you are not at risk. And and we don't have enough information to know how accurate these are as markers in these tests. I mentioned these are the last, I'm coming to the end now, so it's, okay, Vicky? All right. Natalie, sorry? Still on time? There'll be questions, okay. So as I said, one company, and this is a correct way to go in the long term, have used injury-specific markers. So they've got that correct, where they've taken a very specific injury and said, what are the genetic markers for that injury? They then use what are known as GWAS association studies. And what they've done here is they've used biobanks, these large biobanks that exist around the world. 2 of the main ones they've used are a UK-based biobank and a North American-based biobank. One of the problems with their approach from a commercial point of view, I think it's important because it says, right, this is possible variants that need to be investigated further, is they have used the various diagnostic codes in these biobanks to phenotype the individuals. Now, some of these diagnostic codes, and Jeroen can maybe talk more about it afterwards, are quite specific, but many of them are very general. So if we take Achilles tendon, there is 1 or 2 diagnostic codes that are used, but it can be from bursitis to peritendinitis to tendinopathy to rupture. And if you look at the list in the papers where they list what the conditions linked to those diagnostic codes, it's heterogeneous. It's heterogeneous. There are different pathologies. So the problem here is that merely using diagnostic codes is not enough. Now, some of this the disease things, they have used more specific criteria, and that's good. So that's the first thing. In most of these conditions, the diagnostic codes have been used without a very clear indication, being very specific to make sure that the pathology is homogeneous. The other thing is, as I've mentioned, the biobanks are coming from either North America or the UK. So guess what the population group is predominantly? European. So we're looking at from 80% European to 100% European, depending on which biobank it is. Now, what I've shown here is a list of the conditions, the injury, and the terminology I've put here are what they've used. Okay, so that's what the authors have used or the company has used. And going through the literature, because I often don't cite which are the variants that they use, but we were able to trace out through the scientific literature. And then, so for rotator cuff injury, they use 21 variants. For Achilles tendinopathy, 5 variants. And so it goes down. However, the effective allele, so that's the allele that is associated with that condition, in many of these variants is very, very rare. And what I've shown in red are, for example, ACL and PCL injury. Out of the 3 variants, all 3 are rare. I mean, very rare, like less than 0.1% in the population. Ankle injury, all of them. So a lot of the injuries, they're using very rare variants, and also variants that are not found in all population groups. If you look at the injuries in black, that there are more common variants, there also is, many of them are also population specific. They're common in a limited number of population groups around the world, and they have not been shown to be associated where it's been tested when repeated in independent investigations. So I haven't gone into all the detail of this, but of all of these variants that are listed here, there are probably 3 that could be further investigated. Okay, so even though this is GWAS, even though it's injury specific, just it's still premature to include these variants within tests. I would like to end off, what can we actually do? So you've probably seen that I wouldn't waste my money on a commercial test, genetic test. But a genetic test for injury. Is that specific enough? Thank you, Alison. She keeps me honest. But this is a type of question that I've often had to deal with, where a clinician will say, look, I need some advice on the following athlete. They've sustained rupture of one of their shoulder. Is it in the shoulder? Is that right? Tendons. There's a history of other tendon ruptures, etc. Is there a genetic component? What do I do? And the answer is actually quite simple. What one would have to do in a situation like that is to exclude all the other possible risk factors. So speak to the trainers, speak to the clinicians. Maybe they're playing a position and there's been errors in they don't know how to tackle properly. So Sharif needs to go and chat to them, okay? There could be some reasonable explanation of why they've had those injuries in the first place. It's got nothing to do with genetics. Once you have excluded any non-genetic explanation, then it is reasonable to assume that there might be a genetic component, that person is susceptible to particular injuries. So what one can do in this situation is, through the clinicians is to say, right, what are the common injuries for that sport? So if it's an acute injury or acute rupture of a tendon, what are the common acute ruptures that are common, say, in rugby or soccer or whatever? And we all know that prehabilitation works, and that prehabilitation reduces risk of injury. The problem with prehabilitation is that a lot of the programs are set for a whole team. And when you're doing it for a lot of people, your specificity decreases because it's mass participation. But if you suspect that somebody is in particularly more prone, you could do some more personalized rehabilitation with them to reduce risk. You'll never totally abolish it, but hopefully you can reduce it. So you really don't need a test. You can logically say, right, actually, I think it's reasonable to think this person is susceptible. And what can we then do to reduce risk? Not prevent, reduce risk. So in conclusion, musculoskeletal tissue injuries are multifactorial. There is no single cause. Caused by a poorly understood complex interaction of numerous intrinsic, which include genetic components and extrinsic factors. The genetic factors probably play a very important role in explaining the inter-individual variation to susceptibility to injuries. It's polygenic. Polygenic means there's no single gene. There are many, many, many. Okay, and that also is an indication that you can't have a test of 3 or 1. Okay. However, our current knowledge and understanding is in its research phase and it's in its infancy. So based on the current evidence, it remains premature to market any commercial genetic test to determine susceptibility to musculoskeletal tissue injuries. What I believe is an appropriate current approach is we can do personalized medicine without a genetic test, as I explained to you in the previous slide. And I'm now done. Thank you very much.